Alright, geometry. Today we're going to be looking at segment partitions. The notes are a little bit longer than usual, so bear with me here. But it should look kind of familiar to the midpoint formula stuff. We are finding points again on the line segments, only this time instead of finding the ones directly in the middle, we can find anything we want. Like we could find a point 1/3 of the way down the segment or 2/5 of the way down the segment. It's just whatever we want to find. This allows us to do it. It's a little bit more complex, but it's a lot more powerful than the midpoint formula. So let's jump right into it. The first thing we need to talk about is directed line segments, because these segments are going to be going from point A to point B or from point R to point S, whatever they happen to be. So a directed line segment is going to be a line segment with an associated direction. So exactly like it sounds. So it's not just a two-way thing. We're actually saying from A to point B. So point A is going to be, in this particular one, the initial point. And it's going to have coordinates of, let me get that out of the way. It's going to have coordinates of x sub 1 and y sub 1. So this looks kind of familiar to what we had in the midpoint formula. The difference is going to be that this time the order is going to matter. Alright, so point B, if point A is the initial, point B is going to be the terminal point. And the coordinates there are going to be exactly what you think they are, x sub 2 and y sub 2. So let's get those on there. Alright, so we're going from A, and then we're scooting along this to B. A is our initial point, B is our terminal point. So we've got a run, which is our horizontal distance, and a rise, which is our vertical distance. The order does matter here this time. So our run is always going to be x sub 2 minus x sub 1. So this is unlike the distance formula where we had we squared things, so it didn't matter what order we subtracted them in. And then obviously with the midpoint formula we were adding two numbers, so it doesn't matter what order we add them in, because addition is commutative. But this time it does matter, because the positive or the negative, it matters. So our run is x sub 2 minus x sub 1, and our rise is going to be y sub 2 minus y sub 1. So this basically tells us how far are we moving either left or right, and how far are we moving either up or down. So let's practice this just a little bit. So we want to find the horizontal and the vertical components of directed line segment PQ to the left here. So I think the first thing we need is to know what points we're dealing with. So P is 1 over to the right and 2 up, so that's at the point 1, 2. And then we've got point Q, which is a lot over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 over, and 1, 2, 3, 4, 5, 6 up. So we're looking at the point 10, 6 right here. Alright, so now that we know our points, we can figure out our rise and our run. So our horizontal component here, we'll just call that H, is going to be 10 minus 1, which is going to equal 9. And then our vertical component, we'll call that V, is going to be 6 minus 2, which is going to equal 4. So as the directed line segment moves along from P to Q, it moves to the right 9 because this is a positive number, and it moves up 4 because this is also a positive number. So right 9, up 4, that is our run and our rise. Okay, see if you can do number 2 here. Okay, so the reason we're talking about rise and run is we are going to want to partition segments. So to partition a segment means that we are going to either separate or divide the segment. That's just the definition of partition. So we can partition a line segment into smaller segments and compare their lengths as a ratio. Especially, so we're going to have a segment that's broken into smaller parts. We're going to be able to take a ratio of part A to part B, or we're going to be able to take a ratio of, say, part A to the whole thing. Okay, so AB is partitioned into 5 congruent parts. Give each ratio. So we want to find the ratio of AP to PB. So if we look here, we can see that AP is 3 units long, and PB is 2 units long. So our ratio of AP to PB is just that. It is 3 to 2. So that's our part-to-part ratio. And if we want to talk AP to AB, then we're talking about the part to the whole thing. Well, 3 plus 2 is 5. So our ratio of AP to AB is going to be 3 to 5. AP didn't change, but now we're looking at the entire segment instead of just part to part. Okay, moving along. Let's identify a couple ratios here. Let's look at number 4. We want to identify AP to PB. Well, AP is 1 unit long and PB is 2 units long. That's usually the first step, just to see what you're working with here. So that means that AP to PB is just 1 to 2. Now we want to look at AP to AB. So AP to AB, that's the small part to the whole thing. 1 plus 2 is 3 last time I checked. So that means that our ratio is 1 to 3. All right, see if you can do number 5 here. Okay, so now let's get into it. Let's find some coordinates. So what if we want to find the coordinates of a point that partitions a directed line segment into a given ratio? So this is the part that is just like the midpoint formula. We're going to actually use this to find some points. It is a little bit more complex because it's more powerful. We can't just find the middle point. We can find whatever point we want. So the first thing is, step 1, we need to write the ratio as part to whole. So it has to be part to whole. This will not work, and we're going to write it, instead of like the colons that I wrote it with up here, we're going to write it as a fraction because we're going to be multiplying. So part to whole in fraction form. Then we're going to deal with our x value and our y value separately, but we're going to do them exactly the same way. So just don't get your x's and your y's mixed up and everything's going to be fine. So we're going to multiply the run by this ratio that we just found in part 1, and then we're going to add that to our initial point x coordinate. And this is going to be the x coordinate of the new point. And then we're going to do the same thing with the vertical component here. We're going to multiply the rise times our ratio from part 1, and then that's going to give, and then we're going to add it to y sub 1, our initial point, and that's going to give us the y coordinate of the new point. Okay, so this seems complicated, but it's really not that bad. So number 6, we are given a directed line segment AB. So our initial point is A, and our terminal point is B. So I think that the first thing we need to do is we need to figure out where we're dealing with. So A is 1, 2, 3, 4, 5 to the left and 1 down. So -5, -1. And point B is pretty far over there. 1, 2, 3, 4, 5, 6, 7 over. 1, 2, 3, 4, 5, 6, 7 up. So we are at 7, 7. Okay, now we know our points. So step 1, we need a ratio. So this is saying to find the coordinates of P such that AP, and P is going to be somewhere around here where my mouse is, AP to PB is 1 to 3. So if this segment is 1, and we pretend that P is right here, so we've got this AP is 1, and this PB is 3, then the entire length is going to have a multiplier of 4. The ratio part is going to be 4. So we can put this as AP to AB, so that's our part to the whole, is 1 to 4. So the small part is 1, the entire thing is 4. And now we just need to find our x coordinate, and then we need to find our y coordinate. So our horizontal component, our rise, well, we're going to multiply by 4, and then we're going to take x sub 2 minus x sub 1. So 7 minus a -5, that's the same thing as plus 5, and then we are going to add that to the initial point. So that is going to be plus a -5. So right here we've got 7 plus 5 is going to be 12, and we take a quarter of that. So 12 divided by 4 is 3, and then 3 minus 5 is going to be -2. So that's going to be the x coordinate of point P. And then we can do the same thing with our y coordinate. We're going to start off with our ratio here, 1 to 4, and then we're going to take y sub 2, which is 7, minus y sub 1, so minus a -1, so that's going to be plus 1, and then we're going to add that to the initial point, so plus -1. Okay, so 7 plus 1 is going to be 8, and then 8 divided by 4 is 2, and 2 plus a -1 is a positive 1. So that means our point P is going to be at the coordinate -2, 1. And let's see where that fits on here. So we go over 2, up 1. So we're on the line. That's always a good sign. And it's going to be right there. So we will call this point P. And we could use the distance formula actually to double check. I'm not going to do that here. But AP should be some distance. I don't know what. And then PB will be 3 times as long as that distance. And then if we want to find that distance AP again and then look at AB, that's going to be 4 times the length of that distance. Okay, try number 7 yourself. See if you can find the point S. So this time be careful, we're going from R to T, so we're starting on the right and going down, and then S is going to be somewhere in here. See if you can find that point S. Okay, we'll skip number 8 for time. We have a formula here. It's just the same thing that we're doing, only putting it in formula form. So given a directed line segment AB with coordinates of x1, y1, and x2, y2, if point P partitions AB such that the ratio of AP to AB is K, so that's our fraction that we found, like the 1/4 up there on number 6, that is going to be our K. So the coordinates of point P are going to be K times the quantity x sub 2, whoops, I should be doing this in an equation box instead of a text box. Okay, so we've got k times x sub 2 minus x sub 1 plus x sub 1. So that's our x coordinate, so we can put a comma there now. And then our y coordinate is going to be k times y sub 2 minus y sub 1, and then plus that initial point again, y sub 1. Okay, so that's a formula for it. Let's do one more example together. So given that AB is going to be from A to B, so A is at 3, -1, B is at 8, 14, and our ratio of AP to PB is 2 to 3, and we want to find the coordinates of P. Okay, so we've got our A this time, we've got our B. We need to find this K, this ratio. So our K is going to be equal to this AP, which is 2, to the whole thing, which is 5. So our ratio is 2/5 here. And now we can find our x value and we can find our y value. So let's find the x value first. So we know that our x value, and I'll just put this as x sub p. We know that this equals k, so 2/5 times, and we have to make sure we do this in order, so we're going 8 minus 3, and then plus that initial point again. Okay, and then just make sure your order of operations is correct. So 8 minus 3 is 5, 2/5 times 5 is 2, and then plus 3 makes it a 5 again. So our x sub p, which means just the x coordinate of point P, is going to be 5. Okay, let's do one more here. Let's find the y sub p. So the y coordinate, we're going to use the same ratio, 2/5, and this time we're going to take y sub 1, or I'm sorry, y sub 2 minus y sub 1, so that's minus a -1, and then we're going to add the initial point again, so plus a -1. Alright, so let's make sure we do our order of operations correctly. So 14 plus 1 is going to be 15, and then we want to multiply that by 2/5, which is going to be 6. I did that in my head by saying 15 times 2 is 30. 30 divided by 5 is 6. And then 6 plus a -1 is a positive 5. So that is our y coordinate. So point P is going to be at the coordinates 5, 5. All right, one more, see if you can do it. Try to find number 10 here. You've got MP, so we're going from M to P, and you want to find N there. So do that. Bring your questions for tomorrow. We'll do a couple more examples, and I'll see you then.